Good afternoon and welcome to the Cybergenetics webinar about how TrueAllele works. This is the first part, and I'm Dr. Mark Perlin from Cybergenetics, and this particular webinar is organized to answer questions that people have had over the last half year from talks, webinars, and discussions. Let's begin by looking at evidence from a case that I was involved in. This is biological evidence. It's similar to what you get in your lab. On the left, labeled Q for questioned items, are 4 shotgun shells. And the situation in this case is that a married couple was found murdered in their home, and the main suspect happened to be their son. Indicated on the right is the family pedigree of the father and mother, shown in red, who are deceased, and their son, who's shown in blue and is indicated as S for son or suspect. The forensic question that we would be asked, or you would be asked, is did suspect S contribute his DNA to the biological evidence Q, the shotgun shells? And I'm going to show you how you would use TrueAllele to answer this question. So in your laboratory, you'd begin by taking the shotgun shells, you'd swab them, extract the DNA, amplify with PCR the DNA material, separate them out on a DNA sequencer, and detect the peaks on a genetic analyzer. And what you'd see is the sort of data that we had in this case, which is a complex pattern that's clearly a mixture of more than one person, given the number and complexity of the alleles. So that's our starting point. That's the data. Now, what a TrueAllele analyst would do at Cybergenetics or in your lab, starting on the left, they would take the .fsa files and put them into their view station, a large screen Mac or Windows computer, and then moving from left to right, upload that data as quality check peaks onto the TrueAllele database server. You would also ask questions, asking the computer to solve this data, maybe as a 3-person mixture, or ask some other questions. And then continuing with the arrow to the right, the interpretation of modules that you would have that typically have another 12 processors on them would start working. So one of the 8 to 80 parallel processing computers that you have would pick up that question and independently start solving that problem, while another 50 questions would be solved in parallel on maybe different cases. So what is the computer doing? The computer has a Bayesian probability model. The Reverend Thomas Bayes created and proved a very interesting theorem 250 years ago. And what he showed was, if you start with some prior belief, and that's indicated on the right in brown, and you update that with a likelihood function that can explain data that's indicated in green, then the posterior probability, the probability that you would obtain after having seen that data, indicated in blue, is what you would then believe. So that your belief after seeing the data is the likelihood, a factor that interacts with the data, times your prior probability. And there's a constant called the data constant that makes sure everything adds up to 1. The sort of variables that we have in TrueAllele, which I'll start going through now, are background noise, PCR variation of peaks, mixture weight, PCR stutter, relative amplification, genotypes separated into different contributors and loci, differential degradation, and so on. It's important to note that TrueAllele doesn't need any calibration. It's a rich enough Bayesian model that it learns information about stutter and other parameters from the data, and in that way it's not locked in to an incorrect calibration based on old data that may have little to do with the casework data. Let's start with background noise, and the first thing I want you to do is ignore all this math that is described in papers, and let's just focus on that one circled parameter, tau squared. So that's the parameter for the background noise. And if you're conversant with Bayesian statistics, you'd know how to use the math that's described here and in our 2009 paper in +1 to calculate tau squared. What is tau squared doing? It's a parameter for the background noise. It's what, having looked at the data and having a model of how background noise from the instrument behaves as analytical noise, it works out something like the right half of a bell curve, and it provides a probability distribution that on each experiment for each peak describes background noise. And that's why no analytical threshold is needed, because we're modeling the data using statistics in order to work out what the background noise is. And this is done for each experiment. Another important source of variation is PCR variation, and that's described in papers including the JFS paper described above. Again, ignore all the other math that's given in the paper and just focus on what's circled in red, which is sigma squared times the peak height. So sigma squared is the variation parameter for stochastic or peak height variation. And what you can see is that lower peaks, as shown on the bottom right, have less variation, whereas taller peaks, as shown in the center of the screen with that bell curve, have broader variation. So because PCR is a counting process, its variation varies with peak height. And again, the computer works out what that variation is, what the sigma squared parameter is, from this Bayesian model, depending on what the data is trying to tell it. And that's why no stochastic threshold is needed. It's worked out directly from the data, customized to each experiment. Another important parameter is mixture weight. We first described this and wrote the math down in a paper in 2001 in the Journal of Forensic Sciences. And in this case, you can see what TrueAllele has done. It's separated out the mixing proportions of the three contributors of the father, shown in gray, as a major contributor, about 60% with a wide spread. The son, shown in orange, with an average of about 30%. And the mother was also a contributor, a little under 10%, shown in blue on the left. And what this picture shows is that all parameters in TrueAllele are probability distributions. So here you're seeing the shape of the bell-shaped like curve for the three mixture weights of this template. Now, it's not enough for accurate modeling to just give the mixture weight of the template. We can do a lot more, and that's done with hierarchical modeling. All hierarchical means is there are layers. So starting from the top here, we see the experiment data indicated by D for one of the contributors for the different loci and the different experiments. The locus weights that you could calculate from peak heights are indicated in the next level underneath with W sub K1, W sub K2. This is all for the K contributor. And they're all samples from the template mixture weight, indicated towards the bottom as W sub K, and it has a prior probability. And when the computer solves these problems, it sort of ping-pongs back and forth with the data informing the locus weights, which then help determine the template weight, and the template weight helps determine the locus weights, and so on. But with TrueAllele, with hierarchical modeling, you don't need just one parameter for something like mixture weight. You can customize to each experiment as well. PCR stutter is a phenomenon that I first started writing about in 1995 in the American Journal of Human Genetics. And this picture is taken from a talk I gave at SWGDAM in 2003, where I talked about stutter. This is for locus D18. If you look on the x-axis, you see increasing allele designation, and the y-axis is showing the stutter proportion. And as you know from your experiments, as the allele length increases, the amount of stutter on average increases. So TrueAllele models that green line with two parameters. It has the slope and an intercept parameter, and it also has the variation shown as the distance between those red bars as a standard deviation. So it takes several parameters to model PCR stutter. And this again is done for each different experiment. So it's customized to the data for each marker. Similarly, TrueAllele models relative amplification. This is the tendency as DNA fragment size increases to have a fall off in amplification efficiency. So here again, there's a linear model, and you can see that negatively sloped line in green with variation around it. And here again, that's done for each locus and for each experiment, as I described in this talk in 2003. The genotype pattern is perhaps the most important part for getting started and the most intuitive component. And this was described in our 2001 paper in JFS. Again, ignore the rest of the math and all the Greek letters and just focus on what's in that red rectangle. And what you'll see is there's a summation sign of weights times genotypes. So what that means is that the allele pairs are added up together based on their relative weights or their quantities to form a pattern. Here we see more of genotype 811 shown in blue as a pair of alleles, a little bit less of genotype 8 and 9 shown in orange, and then a third genotype, a 9 and a 10, shown in green. And these allele pairs are added up in accordance with that equation shown in red and plugged into the overall Bayesian model to help find and separate out the genotypes. Now, that pattern is not enough, even though it looks close to the data. The most important part of modeling in STR analysis is modeling the variation. And variation is introduced at multiple layers. And when you have multiple layers, that's where hierarchy comes in. Each pattern can be then varied slightly based on the phenomenon. DNA quantity, as I show in the center. Degradation. Mixture weight introduces more variation in the pattern. So these patterns start getting distorted to account for the variation in the PCR process. Relative amplification, stutter, the capillary injection, until finally the succession of patterns shows the process transformation and culminates in an explanation of the data pattern where the theoretical model is looking very close to the data pattern with good genotype explanations and very far from it with poorer genotype explanations. In order to explore all these variables, we need a search method. Ordinary calculus and integration doesn't work because there's more than 2 or 3 variables here. I've already described, if you look at all the hierarchical levels, the way one mixture weight parameter is now customized to maybe 15 different loci. There are many, many variables if you account for hierarchy. And so Markov chain Monte Carlo is the standard method for solving these problems. The beauty of the method is that easy for a computer, local probability choices lead to a global solution that maps the entire probability space. Every cycle, whether it's 5,000, 10,000, or 100,000 cycles, TrueAllele will visit all 100 variables and do the operation I have represented in this picture. It begins in a current state, shown in blue in this multidimensional parameter space, and then a next state, shown in green, is proposed. If the next state has a higher probability, if it's better than the current state, the computer will move to those parameters. However, if that next state is not as good, then a choice gets made, and there's a transition probability shown on the bottom, which is essentially the probability of that next state in green divided by the probability of the current state. So that transition will occur to the next state even if the probability is less, with that ratio of the probability of the next state to the current state. So if the next state is almost as good, then the probability is almost 1 that it will go there. So in this way, Markov chain Monte Carlo can search 100 dimensions, visit the entire state. It doesn't just go to the best answer, it explores all answers based on their relative probabilities. Now, when Markov chain Monte Carlo is done, there's a joint probability distribution. This is all the variables together, the 100 or 200 variables, in a high dimensional space. And that's the answer over all the parameters. For example, here for a genotype I show on the left, maybe there's 3 contributors and there's 10 loci. That would be 30 genotype parameters, each its own random variable. In this space, there's the genotype, there's mixture weight for contributor and loci, PCR stutter for different loci, other PCR artifact variables, variance parameters for baseline and peak variation, all these hierarchical variables. And all of this needs to be solved for to accurately describe the PCR process. But that's not what's going to help us in reporting an answer. What we need to do is reduce the dimensionality and marginalize to separate out the different variables. Marginalization works like this. Imagine you have a 2-dimensional table, say it's 2 variables, of rows and columns. If you add up the columns to get 1 row, you've marginalized those 2 dimensions by adding them up into 1 dimension. With TrueAllele, this happens over hundreds of dimensions, and that reduction to 1 variable is done by summing or integrating, adding up over all the other variables. You have to solve for those variables in order to be able to account for them. So here, for example, what would happen is if we took a look at the 2nd contributor, indicated as in red as the 2nd row, and the 8th locus, then by marginalizing that joint probability distribution down to just that 1 genotype, the objectively inferred genotype at locus 8 for contributor 2, you would obtain the probability distribution over a few allele pairs that you see on the bottom here in that blue bar chart. So that's what it looks like when TrueAllele separates out the data into its component variables, including each genotype for every locus and for each separated out contributor. Now the next task is to do something with these objectively inferred genotypes for each contributor. And now what will happen on the computer, starting on the right, is the computer, having solved a problem typically for about 2 hours in most of the lab's high throughput modes, it will then write, that one processor will write its answer onto the database in the center, and then a user will go to their view station on the left to work out the match statistics. The match statistics are based on the likelihood ratio, which is the standard measure of DNA information in forensics, including DNA. It was originally developed earlier than the 1940s, but in its current form was developed at Bletchley Park as part of the code-breaking unit that Alan Turing ran as the mathematician and the person who'd be known as the father of computer science and artificial intelligence. The LR, or likelihood ratio, measures how data change and how data changes our belief. It's a ratio of probabilities. No matter how you write it, there's always a ratio of probabilities in there. The information is the number of zeros of a logarithm base 10 of the LR, named the ban. This picture just shows these large mass-produced computers that helped crack the German Enigma code during World War II, and part of the process used likelihood ratios. On the bottom, you see a scale where 0 is a likelihood, in log units of ban, 0 is a likelihood ratio of 1, plus 6 is a 1 followed by 6 zeros, or a million, 12 is a trillion. Going to the left is a number minus 6, which is 1 over a million, minus 12 is 1 over a trillion. In the context of DNA, when you're comparing genotypes, a 0 is inconclusive, whereas positive numbers provide support for inclusion, and negative numbers on the left provide support for an exclusion. So our hypothesis, again, based on our question, is that suspect S contributed his DNA to biological evidence Q. And as a known, we already have the suspect's genotype. It was, say, worked out as a reference sample. And we know from the 2 peaks that we saw in that reference sample that his allele pair is the genotype little s with allele values A and B. Okay, so we're going to assess this hypothesis. The odds form that Turing and Jack Good, his associate, formulated and wrote up in 1950 is that the likelihood ratio is a ratio of odds. Here, odds mean like betting odds. And if the odds are 9 to 1 that the Steelers will win, that means there's a 90% chance they would win and a 10% chance they would lose. So the numerator is the odds of the hypothesis after you've seen the data. That's what that bar means. H bar D is the odds of the hypothesis given that you've seen the data. D here means data, divided by the odds of the hypothesis before you've seen the data. This is a Bayes factor. Turing just called it the factor. And it shows the change in belief in that hypothesis from the data. It's also called a likelihood ratio because another way of rewriting it with Bayes' theorem is in one or two steps in some algebra is that it's the probability of the observed data conditioned on the hypothesis divided by the probability of observing the data conditioned on the alternative hypothesis, H bar. And the math and all the derivations are available in a paper that I wrote for a Promega talk in 2010. It's on their website and on ours. So I'm not going to show any proofs. You could read about them in the paper if you care about. If you had single source DNA, then H would correspond to H sub P, if you're familiar with that terminology, and H bar would correspond to H sub D. This is the likelihood form. Now, this is a great way to write it down, but it's not the best way to calculate it. To calculate it, we're better off using those genotypes we've already inferred. Remember, TrueAllele can separate the mixture into genotypes for each contributor. Now we can take advantage of that. So the numerator, that probability of the data given the hypothesis, can expand into a sum, that's the symbol sigma on the left, of each allele pair value, little x, that belongs to the set of genotype values, capital G, of all the different possible genotype values. The first term shown in green is the likelihood, the probability of the data, given that the evidence genotype random variable capital X is equal to or has the value of that allele pair little x, times the probability that the random variable X is equal to that value little x given the hypothesis, which is a prior. So essentially that splitting with genotypes looks like likelihoods and priors. In the denominator, it turns out after some algebra that the probability of D given that someone else contributed their DNA is just, again, the probability of D, so I won't bother with that algebra. Now, in the numerator, notice what it's saying. We have all these likelihood terms based on what the data is trying to tell us in green, and then the prior terms in brown have nothing to do with the data. They're based on our hypothesis. But what was our hypothesis? It was that the individual with the suspect S with genotype little s is the contributor and nobody else is. So that term will take on the value 1 for the suspect and 0 every place else. And so when we apply the hypothesis, only the term with that value shown in red, little s, the suspect's genotype, remains. So that entire summation of the numerator is reduced to just the suspect's term, the probability of the data, given that the evidence genotype takes on the value S, the suspect's genotype, which is a likelihood, divided by the probability of the data. Okay, so this becomes much easier. We've reduced it to one term, but we want to do more with it. So let's remember from Bayes' theorem that the posterior probabilities are much easier for people to work with and understand than likelihoods, that the posterior probability in blue is proportional to the likelihood in green times the prior probability in brown, with a constant called the data constant in the bottom. If we divide both sides by that prior probability of a genotype and reorganize, then you see, moving that brown from the top right to the bottom left, we have the ratio that the posterior over the prior genotype probabilities is equal to the likelihood over the data. Well, we just had the likelihood over the data. And so in this way, the genotype form becomes the posterior probability over the prior probability. And that's what I've written over here. In the numerator, the posterior is the probability that the evidence genotype is the suspect's genotype, given the questioned evidence data, D sub Q, divided by the prior belief. Now, that ratio was first described in 1938 by Essenmuller for paternity indices, which is the type of likelihood ratio. It's been around for a very long time. It has this nice feature that you can see it. And these are the sort of pictures that we show in court to visualize the LR at a locus as a ratio of genotype probabilities. In blue, we have the evidence probability of one of the contributors to the mixture, and that has a probability of 61% at the suspect's genotype of 8-9, and the prior probability, the chance of a coincidence, was only 4% for an 8-9 genotype value at this particular allele pair. Now notice the math doesn't care which allele pair you're looking at. You could have chosen to compare it with an individual with a 10-11 genotype all the way on the right, in which case the evidence genotype would be a lot less than the Brown genotype, and you'd have exclusionary information. But here, since the suspect's genotype indicated in the red rectangle is an 8-9, that ratio of 60% to 4% is around 15, and that becomes the likelihood ratio at this locus. Multiplying the likelihood ratio together at all the loci is what will give us the final match statistic. Now I want to show you here the match form. This is exactly what you saw before, but there's this new red term shown on the right. The probability of Y, the random variable of the suspect's genotype, the probability that it takes the value of the suspect's genotype given the data. That's 1 for a reference sample. So all we've done is replaced 1, the certainty of the reference profile, with this expression in red, probability that the suspect's genotype is that value S, given the data D sub S from the reference profile. Now interestingly, the numerator is now a product of two probabilities that both have the same value, little s, the same allele pair. The probability that the evidence genotype is equal to allele pair S, given the evidence data, times the probability of the reference suspect having that value, given the data. In mathematics, that's a match term. And we saw there's only one term here because the one on the right is 1. So the math is telling us that we can use the word match, and it's happening because it's all single source. There's no mixtures anymore. The computer has done all the work of separating that out. So we have a match expression in the numerator. The coincidental match in Brown in the denominator is the chance of a random match in the population. So it's a genotype match of evidence and suspect divided by coincidence, and that translates into a very understandable match statement, now as a ratio of match probabilities. And as I wrote in the report, a match between the shotgun shell and the sun is 6 trillion times more probable than coincidence. Again, the 6 trillion comes by multiplying together the likelihood ratios at all 15 loci. The advantage of a statement like that is that it's based on accurate mathematics. The language is plain English. It's understandable to everyone in a courtroom. There are no conditionals to transpose. Bayes' theorem is taking care of that for us. It's just probabilities, no likelihoods in sight. And it's comparing separated genotypes. It's brought us back to the language and the concepts of random match probability or conditional match probability, where we can compare genotypes from one contributor to a genotype from a second contributor to different evidence. Now, I'm showing this to you only because it's general. TrueAllele also does evidence-to-evidence matches. And here, suppose in red that suspect was kinship information. So we didn't know exactly what his genotype was from the data D sub S. Or maybe it's another evidence item. The point is there's uncertainty. So if there's uncertainty, the terms don't all collapse into one term, and now we have a sum of terms of the evidence posterior probability times the subject in red posterior probability divided by the prior probability for each genotype value summed over all the allele pair possibilities for these single contributor genotypes. And it's important to point out, as I say in the bottom, that this summation or integral, if they're continuous variables, of a product of two probabilities divided by another probability, the posteriors divided by the prior, is the standard form of the likelihood ratio in probability theory. if a textbook on measure theory or information theory is devoting a few paragraphs to the likelihood ratio, this is their starting point, not their ending point. And that brings forensic science into conformance with the rest of science. Now, just a few more comments about the likelihood ratio. What I showed you was a single contributor likelihood ratio. There were separated genotypes for each contributor. The TrueAllele processing of doing that separation, whether it took an hour or 2 hours or 12 hours, it did the heavy lifting of doing that Markov chain search over the hierarchical Bayesian model to separate out those genotypes to achieve the simplicity of single source DNA again. Single source DNA concepts like that are easy to understand, they're easy to report, and they're easy to explain to people. And it also makes the direct examination and the cross-examination in court very straightforward. There are no arcane concepts. And it's also legally relevant. The focus is on one person. There's no combination that these three people are in versus something else. In court, there's only one defendant who's being tried at a time, usually not three. It compares genotype with genotype. Now, by comparison, in forensic science, when the genotypes are not separated out and you don't get the power of reducing it to a single genotype at a time, you're now stuck with this unseparated likelihood ratio. And this is where HP and HD come from. So there's a proposition that the random variable X has the value of one person, and the random genotype value Y has little y, the value of another person, and Z is another person with a value. And in the denominator, two of the values are unknown, one's unknown, and then the likelihood ratio of this unseparated data is the probability of data given the prosecutor's hypothesis divided by the probability of data given the defense hypothesis. This is much more complex. And here are some reasons why. I stopped at 10, but there are more reasons. First, the quote data is not really the data. It never was the quantitative data. It's just thresholded data that may be right, may be wrong, and has lost all the information of the pattern, the variation, and the peak heights. This expression with HP and HD is suggestive from Turing's H bar and H as alternative hypothesis, but it's not. It doesn't have a Bayesian foundation, and the math is wrong from a Bayesian perspective. It's suggestive, but it isn't science. The third point is, these are subjective genotype values. You're just plugging in some guesses and hoping to get some number. Also, these guesses use the defendant genotype in the calculation. This isn't objective. TrueAllele is objective. It calculates the genotypes without knowing the defendant's genotype and only makes its comparisons afterwards. Again, this sort of math might implicate multiple people, which isn't terribly relevant, perhaps, to the prosecution of one person. Clearly, there's no separation of genotypes. This is looking at all the data together or thresholded alleles, whatever it's looking at. It's a very incomplete statement. It ignores most of the data. Clearly, if you're ignoring most of the data, the answer you're going to get is inaccurate. And studies that compare these simpler likelihood ratios with TrueAllele show that they don't agree with each other, and they're often inaccurate if you look at the validations. There are hundreds of thousands or far more possibilities of what genotypes, stutter parameters, all sorts of parameters can be that can explain the data. These formulas are only considering a few, 2, 3, 4 possibilities out of the millions of possible possibilities. They're not a thorough method. They do not thoroughly evaluate data. There's also the issue that there are many hypothesis formulations. There's more than one way of formulating HP and HD. You can have a dozen different formulations, and what you present can be subjective and become very complex. The result of all of this is that this type of likelihood ratio and its language with its conditionals, not using the proper data, not separating out genotypes, and using limited arbitrary hypotheses are very difficult to state or explain. And as a forensic analyst, this might not be the sort of area you want to get into in court, whether you're being asked questions by the prosecutor, the defense, or even the judge. So, part 2 will be continuing next time with dropout and degraded DNA. Hopefully, we'll have time in part 2 to wrap up with this and without needing a part 3. And we'll be able to talk about kinship and DNA databases. In the interim, if you can, on our website at Cybergenetics, if you look at the information tab and the presentations page, 2 of the more recent presentations are 40-minute talks that I gave in the Netherlands, which talks about the science of DNA interpretation with TrueAllele and of mixtures. And then another talk that I gave a few weeks ago at the Promega meeting that talks more about the software. And they're complementary talks, and they're YouTube videos of the narrated PowerPoints that you might find helpful. So at this point, this would be a good time to start taking questions.